going to finish up the homework set here for 3-7. We're working on number 29. Limit x goes to 0 from the right of 1 over x minus 1 over e to the x minus 1. All right, so if x goes to 0, 1 over 0, and we're approaching 0 from the right, so this is going to be a small positive number. This looks like fixed over 0, both of them being positive. It's going to go to positive infinity. So this goes to infinity here, minus, now e to the 0 is approaching 1. All right, let me draw e. Here's e. At 0, it's 1, but we're approaching 0 from the right, so we're always a little bit above 1. Coming in like this, the y value is always a little above 1. So this number right here is approaching 1, but it's always a little bit bigger than 1. And then we subtract 1. This is going to be a very, very small positive number. Okay, it's approaching 0, but it's positive because that number is bigger than that number. So that's a very small positive number. And so you have a fixed number over something approaching 0, but it's always positive. That's a positive over a positive. That's going to give you positive infinity again. So you have fixed over 0, both being positive. So it's the same situation as this one. So this is going to be infinity over here. So we have basically the form of infinity minus infinity. All right. If you have infinity minus infinity, what we're going to do here, because we have fractions, is we are going to try to get a common denominator. So I will multiply the top and bottom of this one here by x, and I'll multiply the top and bottom of this one here by e to the x minus 1 over e to the x minus 1, and that'll give me my common denominator, and I'll put them together. So not doing any L'Hopital or anything yet. I'm just trying to convert this. If I do e to the x minus 1 times 1, I get e to the x minus 1. And then if I do x times 1, I get x, and I'm subtracting that, so minus x, all over my common denominator, which is now this times this. So I write x times e to the x minus 1, like that. Now if I just check to see what's happening here, as x goes to 0, this is approaching 1. 1 minus 1 is 0. Minus, this is approaching 0, so 0. So I have 0 minus 0, that's 0 on top. And then e to the 0 is 1. 1 minus 1 is 0. That's approaching 0 also, so the bottom is approaching 0. So I've transformed a problem that once looked like infinity minus infinity just algebraically into a new problem where it's 0 over 0. That allows me to use L'Hopital's rule. So I come in here with L'Hopital. I take derivative of the top, derivative of e to the x is itself. Derivative of 1 is 0, derivative of x is 1, so it's minus 1 there. Over, now on the bottom you have to be a little careful because you have a product rule. You could also distribute this through, but you'd still have a product rule. So I'm just going to leave it like this. Derivative of the first one is 1 times this one, so e to the x minus 1, plus the derivative of this one, which is just e to the x, times the first one. All right, so let's see what happens here. We have x goes to 0, e to the 0 is 1, 1 minus 1 is 0, the top is 0. The bottom, let's see here, we've got e to the x, that's going to be e to the 0, that's 1, 1 minus 1 is 0. E to the 0 is 1 times 0, so we get 0 on the bottom again. I'm not liking the looks of this. Limit x goes to 0. I'm going to apply L'Hopital's rule again. Yeah, I'll just do it just the way it is here. Derivative of the top. Okay, so derivative of the top is just e to the x. Derivative of the bottom, I have to do term by term. And this is a product rule right there between those two. So derivative of e to the x is itself. Derivative of 1 is 0. Now product rule. Derivative of the first one, so this is plus. The first one is just e to the x times x plus. Now derivative of this one, 1 times that, e to the x again. It looks like this is getting messier, but notice at this point that I can factor an e to the x out of the denominator. These all have e to the x in them, so I factor out an e to the x. I'm left with a 1 here, an x here, and a 1 here. And then I can cancel these e to the x's out, put a 1 there, and now let x go to 0. And you can see that if I let x go to 0, this is going to go to 0. I'm going to get 1 over 1 plus 1. It's going to be 1/2. So I had to do L'Hopital's rule twice there. Twice? 3 times? What was that? Once? Twice? Yeah, just twice. But I had to manipulate things algebraically first and then stick with the L'Hopital until I could get that e to the x to cancel. So infinity minus infinity, we turned it into 0 over 0 by collecting and getting a common denominator. 31. Limit x goes to infinity of x minus natural log x. All right, so what happens as x goes to infinity? Well, this goes to infinity minus natural log of infinity. So take a look at the natural log function. Here it is. And we know that as you go to infinity, this thing grows without bound. It goes up to infinity. So we know that this goes to infinity also. All right, so infinity minus infinity, we need to work on that. Now on the last one, we got a common denominator. And on this one, we can't because there's no fractions. But what I will do is I will try and turn this subtraction into multiplication by factoring. So I'm going to factor an x out, even though it doesn't look like I can. This will be a 1 minus, now if I factor an x out of here, even though there's not an x there, I could write it like this. Now that's a little tricky, but let's just check to see what happens here. If I multiply this through, I get x, that's this. Then this goes over to this, and the x that's here is going to cancel out with the x here, and you'll be left with natural log x. So that's a clever way of factoring out an x. And now let me just check to see what happens here. As x goes to infinity, this is infinity, so I have infinity, times over here, all right, 1 minus, now natural log of infinity, that goes to infinity, so this little piece goes to infinity. On the bottom, it goes to infinity. So I need to figure out what that's going to. I don't know what it's going to yet. So I'm going to do a little work on the side here. This is like scratch work. I'm trying to figure out what's happening to this as x goes to infinity. So I'm focusing all my attention on this piece so I can figure out what this is. Now here we have infinity over infinity. So I can use L'Hopital's rule. Within my scratch work, I'm using L'Hopital's rule. I'm going to take the derivative of the top, derivative of natural log of x, 1 over x, and then derivative of the bottom, which is 1. Now I don't need that 1 on the bottom, so this is just 1 over x. And as x goes to infinity, this gets big, the numerator stays the same, so you have a fixed over infinity, that goes to 0. This goes to 0, so that goes to 0. We know that this limit goes to 0. And what happens here is you get infinity times 1 minus 0 is 1. Infinity times 1 is just infinity. So this limit is infinite. Okay, 33. Limit x goes to 0 from the right. of x raised to the root x. All right. So what's happening here? These problems are very different than what we've done before. We're going to get a different type of indeterminate form. I think I said x goes to infinity. I meant to say x goes to 0. So what happens? This goes to 0, so we have 0 on the bottom. And then it's being raised to the square root of 0, which is still 0. 0 to the 0, that is an indeterminate form. And the reason it is because we know that anything raised to the 0 should be 1, but 0 to any power should be 0. And remember, these are approaching 0. They're not actually 0. That's a little positive number, that's a little positive number. And so there's a battle going on. I talk about this in class, but that is something we cannot just say, oh, the answer is this. We have to do something. But because both the base and the exponent are both functions of x, we're not going to be able to handle this the way we have in the past. We have to do something special. And this is what I showed in class. We call this limit. We just call it something. Let's call it y. We want to know what y is, right? Y is what we want to figure out. And now, because I've created this equation, I'm going to do the natural log on both sides. And when you do the natural log of a limit of something, the natural log can pass through the limit. So here's my natural log, and I'm doing natural log of this, like that. And the reason I do that is because I can now use the property of logs to drop this out in front. So this becomes natural log of y. So I have to write the equation down. Natural log of y equals limit, as x goes to 0 from the right, of root x that dropped out in front times natural log of x. So there's my dropping of the exponent. And now let me just take a look at what's happening. As x goes to 0, I get square root of 0, that's going to 0, times natural log of 0, we're approaching 0 from the right, natural log does that. You can see as you approach 0, it heads out to negative infinity. And 0 times negative infinity is still an indeterminate form, but we know how to handle this one. To do this one, we pick one of these and we drop it down to the denominator. So I'm going to rewrite this as, I'm going to leave the natural log x on top. I'm going to rewrite this on the bottom as 1 over root x. Of course, that would flip back up and become this, but by doing it this way, it's going to behave exactly the way I want. If I let x go to 0 from the right, we know that this part up here goes to infinity. And then we know that 1 over 0, and this is a positive number, right, because we're approaching 0 from the right. This is a tiny positive number. That's a fixed positive number. Fixed over 0 goes to one of three things, but in this case, because they're both positive, we know it's positive infinity. So now we have infinity over infinity. So let's just recap real quick. We started out with a form that was 0 to the 0. We knew we couldn't do that. We had to do natural log on both sides. We dropped the exponent out front. Then we get 0 times negative infinity. We still can't do that, but we can convert that to infinity over infinity by dropping it. And now I can use L'Hopital's rule. So what I'll do is I will write, I still need to write the equation. This natural log of y should be equal to this, and I'm going to use L'Hopital, so I'm going to put, by L'Hopital's rule, that's equal to this limit. Now I'm take derivative of the top, which is 1 over x, over the derivative of the bottom. So I need to take the derivative of this. So let me just remind you what that is. 1 over root x, I need that derivative. That's the same as 1 over x to the half derivative, which is the same as x to the negative 1/2 derivative. I need to do that. So I can just use power rule here. This is going to be negative 1/2 x to the negative 3/2. Right, so power comes out, I subtract 1. And that's just really negative 1 over, let's go 2x to the 3/2. So I just drop the negative exponent down, and it joins the 2. I'm going to use that. That's what's going to be down here for the derivative. Negative 1 over 2x to the 3/2. And the reason I didn't try and convert that back into a radical is because I realize that on top I have 1 over x. I'm going to take this and flip it right? Reciprocal. So this is going to be times, when I flip this, the 2x to the 3/2 goes on top, and then the -1 goes on the bottom, and then I can get rid of that. And so now, I'll write it all down again. I have that the natural log of y equals limit as x goes to 0 from the right of 2x to the 3/2. It's just multiplying straight across here, and then multiply straight across the bottom, -x. And I can actually clean that up a little more, right? That's x to the 3/2 over x to the 1. You subtract, you get x to the 1/2. Right? 3/2 minus 1 is a 1/2. So this just turns into, my goodness, I haven't taken the limit yet. So I have a 2, I have a negative down here. So how about I just make that -2? And then this right here became this, which is really just square root of x. All right, let's let x go to 0. That goes to 0, that's 0, that kills this whole thing. This whole thing is 0. Natural log of y equals 0. This is not our answer. Remember, in the very beginning of the problem, we said, hey, let's call this something, and we called it y, and then we came in with the natural log. So we want to know what y is. We know that natural log of y is 0, so to get y out of the natural log, we're going to use the inverse of natural log, which is e. We're going to take e and raise it to the natural log of y. On this side, we do e raised to this side of the equation. And so you're basically like composing both sides of the equation with the inverse of natural log. E to the natural log of y is y, and then e to the 0 is 1. So y must be 1, which means the answer to this is 1. That's a good problem right there. All right, 35. Limit x goes to 0 of 1 minus 2x raised to the 1 over x. So let's see what happens as x approaches 0. All right, so in here, as x approaches 0, this is going to become very small, right? And, well, that's going to approach 0, and 1 minus 0, that's going to be approaching 1. So the base is wanting to be 1. And then we have, as x goes to 0, we have fixed over 0, which is going to be either infinity, negative infinity, or does not exist. Now, they don't tell us which side of 0 to come in on, which is a little concerning to me. But let's just take a look. If we came in, if we approach 0 from the right, then this would be a positive number over a very small positive number that would approach infinity. So 1 over x would approach infinity. And then what we would have here is 1 being raised to the infinity, which is an indeterminate form. And the reason it's indeterminate, remember from class, is that this is approaching 1. It's not 1, right? This is approaching 1. This is approaching infinity. And so this wants to make this, when you raise something to a big power, it wants to make it bigger, right? If this is bigger than 1, it makes it bigger. If it's smaller than 1, it makes it smaller. So this is a confusing problem. I can really see how a student would get messed up with this. How can I help this? Well, for now, let's just agree that that's indeterminate. Let's now approach 0 from the other side, see what would happen. 1 over x, well, this would be 1 over a fixed number that's positive over a very small negative number, and this would approach negative infinity. And then we would get something like this. I'll put this one over here. This was 1 to the infinity. This one was 1 to the negative infinity, which is the same as 1 over 1 to the infinity. So I could drop it down. And we're still going to have the same problem here, that what does this go to? We don't know what that goes to. So 1 over it, we won't know what that goes to. So we still, either way, we have a problem. The only issue that I have is whether or not that number here is bigger than 1 or smaller than 1. So if I start plugging in numbers that are really small here, right, approaching 0, if this is really small number, let's say it's like 0.000001, if I take 1 and I subtract 0.000001, this number is actually going to be smaller than 1. So this number right here is a little bit smaller than 1, and when you raise it to a big power, when you raise it to a big power, that should actually get smaller. Curious to see what they have as an answer to this one. 35 -2. Okay, well, let's work it, because the base is trying to become 1, all right? So 1 to any power should be 1. This guy's trying to make it either bigger or smaller depending on if this is bigger than 1 or smaller than 1. I know I'm confusing you, all right? So let's just work through this, all right? This is an indeterminate form. You have a base that involves x. You have an exponent that involves x. We've agreed it's indeterminate either way we look at it. So let's go ahead and go about this the same way we did the previous problem. We're going to call this thing y. So let's call this y. And let's take natural log on both sides. I'll pass the natural log through the limit. The natural log will come out here, like that. And then I'm going to drop this out front. So when I drop that out front, get 1 over x, like that, times that. Okay, so what happens here? As x goes to 0, this is either going to go to positive or negative infinity, depending on which side I come in on. And this right here, if that's 0, natural log of 1 is 0. So now it looks like either infinity times 0 or negative infinity times 0. Either way, that's a problem. That's indeterminate. But we know how to handle this. To handle this, we drop one of those down. So I'm going to say natural log y equals limit x goes to 0 from the right, not from the right, x goes to 0 of natural log of 1 minus 2x is going to be on top. And then I'm taking 1 over x, and I'm dropping it down as 1 over 1 over x, which is really just x, right? Just flip that right there, that's just x. Now you could have seen that right now. Like if you just rewrite this, you could just write this whole thing over x and it's the same expression. But I was just trying to use that same idea of taking that and dropping it down. You do 1 over whatever's here, but it still gives us just x. Now as x goes to 0, we already know this is natural log of 1. Natural log of 1 goes to 0, the bottom goes to 0, and we're in business. L'Hopital's rule. Natural log y equals L'Hopital's rule. This, I'm going to take derivative of the top. Derivative of natural log of something is 1 over 1 minus 2x. So that's 1 over what was inside, times chain rule, derivative of what's in here. Derivative of 1 is 0, derivative of negative 2x is negative 2. And that's all over the derivative of x, which is 1. And now if I let x go to infinity, go to 0, that's 0. So you get 1 minus 0 is 1. 1 over 1 is 1. 1 times negative 2 is negative 2. Negative 2 over 1 is negative 2. So this right here, this limit, when we let x go to 0, this whole side over here becomes negative 2. And now, same thing as before, we want to know what y is, right? We know natural log of y is this. So we do e to the natural log of y must equal e to the negative 2. These cancel and you get y equals e to the negative 2. And that's your answer. So this limit is approaching e to the negative 2. As x goes to 0, it's going to that. You could also write that as 1 over e squared. All right, sorry about that in the beginning. I was trying to make it a little more complicated than it had to be, but all right. You should look at the rest of the problems there. You should look at 34, 36, 37, 38. Those are good problems. We are done.